everybody. So now we're going to consider structures that wouldn't be able to be defined as trusses, and we call such structures that support loads as frames and structures that apply loads as machines. So we no longer have the constraint that all the members of the structure are two-force members. So how do we analyze these things? So a good starting point is to just draw the free body diagram of the entire structure, the whole thing. So for example, this one, it looks like this. We don't care about the individual members. All that matters is there's a pin support at A and a pin support at G. So there's a pin at A, which I will decompose. There's a pin at G, which I'll decompose. Okay, and then there's a load over here and another one over here. Okay, and then we can write three equations. Okay, so in the x direction, we got AX, GX, the 8 kilonewtons. In the y direction, AY, GY, negative 6 kilonewtons. Some torque. Well, nothing's happening in Z, but we can sum torque about wherever we want. So how about over here? So about point A, the torque by AX and AY are 0. The torque by GY is 0. The torque by GX is 2 meters times GX in the positive Z direction. The torque by the 8 kilonewton load is 1 meter, then 8 kilonewtons. The torque by the 6 kilonewton load is negative 3 meters and 6 kilonewtons. Okay, so we have three equations, 4 unknowns. We can solve for GX, plug that in here, solve for AX, but we don't have enough equations to solve for both AY and GY. So this is statically indeterminate, actually. So at best, we got this and this. That's it. So what do we do now? So now the next step in the method is different from trusses. So what we do now is break it apart. So for the frame, break it apart. Okay, so this frame is made up of 4 members. So really, you just like break it into its 4 constituent members. Like there are these 4. You just break it apart. And then you draw all the forces acting on each of these members. So there was those reactions at A, which we know this one at least, so that's good. And then there are the reactions at G. And then we know this one. And then let's go back to this member over here. So see how this one is connected to this one? So there's a reaction at point B. We don't know which way, so I'm just breaking it into X and Y components. And then see how this member is connected to this member at joint C. So I'm just going to draw a reaction at C. And I'm just splitting it into components. Okay, and then you see how this is connected to this. So I'm using Newton's third law. If Bx is this way on that member, it's got to be equal and opposite over here. Right? If By is going up over here, it's got to be going down over here. See, action-reaction pair, action-reaction pair, Newton's third law. Same here. This is connected here. So if I draw Cx this way, I have to draw it this way. If I draw Cy this way, I have to draw it this way for this member. right? And then let's say we go over here. If I draw a reaction, let's say like this at E, then where this connects here, I have to draw it equal and opposite this way, right? Because it's an action-reaction pair. And then let's see where else, over here, D. So if I draw this X and Y, then over here where it connects, I have to draw that equal and opposite. Oh, wrong, this way. Okay. So now we have these 4 free body diagrams. And now what about the loads? So there's this 8 kilonewton load here, and a 6 kilonewton load at joint C, but do I draw it here or here? That's a big question. And here's the answer. What happens when you have a load applied at a joint? You draw it on one of the members. Any one, it doesn't matter which one, but only one. So not like you draw it here and here. That is not okay. You just pick one or the other, and you're correct. Because if you reassemble all the members of the frame, then see how this cancels this cancels this, and this remains over here. Okay, so now you have these free body diagrams, and now you can write 3 equations for each free body diagram. So let me spread this out so we have more space. Okay, so there's something I need to point out that will make things simpler. This is not a 2-force member, right? You can't simplify it to a member where there are only 2 forces needed to describe. This is not, but this one is, right? There's only a force acting here and another one acting here. So, for example, if you sum forces in the x direction, for sure, these have got to be equal and opposite. Otherwise, the entire member is going to accelerate horizontally. These have got to be equal and opposite. Otherwise, that member will accelerate vertically. So in other words, it can either be this way or this way, where these are collinear, right, along the same axis. There's no other option. So we could just do that to make it simpler. So for example, I can replace bx, by, ex, ey with something else. So let's say I just draw it in tension. And I'll just call it like B. And this is E, where it's the same magnitude. So I'll just call that B as well. So then if you look here and here, those have got to be equal and opposite. So that means like that, right? And then over here and over here, those have to be equal and opposite. So I can replace this with this. So by keeping an eye out for 2 force members, we reduced the number of unknowns by quite a bit. Okay, so let's get everything to fit on one page. Now let's write some equations to solve this. So let's start with this first one. So some forces in x. We got ax plus cx. That's it. Y direction, ay minus b plus cy minus 6 kilonewtons. Okay, and then let me write all the x and y first. So let's go to this one right here. So x direction, negative cx plus dx plus 8 kilonewtons. Okay, y direction, negative cy plus dy. Okay, now this last one over here. X direction, we got gx minus dx. That's it. And then y direction, gy plus b minus dy. Okay, so let's see. Gx is known. This is known, which means we can solve for dx immediately. Dx is known. Okay, if dx is known, that's here. This is known, which means we can solve for cx right here. So that's known. Okay, and then if cx over here is known, we can solve for ax over here. So this is known. Oh, that was already known anyway. Okay. All right, so now there are the y components. So now let's be clever about how we sum torque to get rid of some unknowns. So if I take a look at it, this has 3 unknowns, this has 2 unknowns, this has 3 unknowns. So I want to focus on where it's easiest, right here. Let's solve for one of those. Some torque about somewhere, let's say point C. Okay, so some torque about point C. So there's torque by dx, which is going to be positive 2 meters times dx. And there's going to be torque by dy, which is in the negative z, so negative 1 meter dy. And then there's torque by the 8 kilonewton load, which will be in the positive z direction, 1 meter, 8 kilonewtons. Okay, and then we already knew dx, which means we can solve this equation for dy, which means we'll know dy, right? And then plug that in here and solve for cy here. So now we know cy here. So now if you look here, there are 2 unknowns. So let's write another equation for torque where we can get rid of one of those. So either some torque about A or B would be clever. So let's say we sum torque about point A. So then the torque would be from B, that would be in the negative z. So that'll be negative 1 meter times B plus 3 meters times cy minus 6 kilonewtons equals 0. Okay, so that's torque about point A. We already know cy, which means there's only one unknown here. Solve for B. Now we know B. Plug that number in right here, which means you can solve for AY. So now we know AY. Okay, and then let's get to the last member over here. We know B right here. So now we only have 2 unknowns left. So we just need to write one more equation for torque where we get rid of either gy or dy. So whichever one, let's say some torque about G. I mean, as a counterexample, if we sum torque about point B, then both gy and dy would still be unknowns. We can still solve, but then there'd be 2 equations, 2 unknowns. If we sum torque about point G, then let me just write that out. Then there would be torque, let's see, that would be 1 meter, positive 1 meter times B, and then negative 2 meters times dy. Since we already know B, then right here, it's easy to just solve for dy, and then plug that in right here, and then solve for gy. Now we know everything, everywhere, right? We know all the reactions for all the members everywhere. And your numbers will depend on how you draw your free body diagrams. So that is also something to point out. Okay, so just practice this new method, and the more you practice, the better you'll get at all this algebra. Okay, so, and let me know if you want to see more examples. I can post more videos. So I'll see you on the next one.